So once again welcome to my YouTube channel, and it is the second lecture on separation axioms. So we are going ahead with this topic, separation axiom in topology. In the first lecture we have discussed the definition and basic properties of a T-naught space. Now we'll do a little bit more about T-naught spaces, and then we'll move on to the T1 spaces. So there is a theorem of T-naught spaces, you can say, that is continuous image of a T-naught space need not be T-naught space. So if a space is T-naught and there is a function from this space to another space which is continuous, then the image space need not be a T-naught space. This is our theorem. So how to prove it? So where we have this need not be, then it is more than sufficient to provide some counter example. So I am giving a counter example here. So I am defining a function f from this you can say x with discrete topology to x with indiscrete topology, where x can be any set. X is any set, and we are defining a function f from x with discrete topology to x with indiscrete topology as f of x is equal to x. This is our function, and this function is continuous. Why? Because for continuity what we need, we are just to show that inverse image of every open set is open. Here we are having only two open sets, namely phi and the set x itself, because it is in discrete topology. And what will be their inverse images? The same, because function is fx is equal to x. So inverse image of x will be x. So inverse image of phi will be phi, and inverse image of x will be x. And here the topology is discrete topology, and we know that in discrete topology every subset of x is open. So why not phi and x? So these will also be. So that means inverse image of every open set here is open here, which makes this function continuous. So this is a continuous function. So this is a continuous function. This is a T-naught space, we know, because for any x not equal to y in x, we are having, you can say, a singleton set x. And this singleton set x is open set because every subset of x is open with discrete topology. So this is an open set, you can say G, such that x belongs to this set and y does not belong to this set G, that means the singleton set x. So that means the space is T-naught. But this space is not T-naught. The image space is not T-naught. Why? Because if you take x not equal to y here, then what you need to make this topology, or you can say this topological space, to be T-naught space, what you need? You need either an open set which contains x but not contain y, or an open set that contains y but not contains x. But unfortunately there we are having only two open sets, phi and x. The first open set does not contain any one of these. The second one contains both of these. So from where can we have an open set which contains one of these and does not contain the other? That is not possible. So this is not a T-naught space. So here is the example of a continuous function from a T-naught space to a non-T-naught space. That means continuous image of a T-naught space need not be a T-naught space. That's what we wanted to show. So this was the first question today. Now we move ahead with more questions. So let us see what next we are to go. I am taking another example. So you take your X to be the set closed to 0 and open to 1, and that is a subset of the set of real numbers. This is open. This is a Klopen interval, closed on the left side and open on the right side. That means 0 is included, but 1 is not included. So this is your set, and now we will have to consider some topology also. So I am taking this topology phi x tau is equal to phi, and all the sets gk of the type sets, you can say intervals of the type closed on left side with 0 and open on the other side, right side, with k, where your k is, it may be 0, greater than 0, not equal to 0, it may be greater than 0 and is less than or equal to 1. Now you can easily check that this tau is a topology on this set X. This is very much clear, you can check it. Now what we are to show that, we will show that this topology, or you can say this topological space X with the topology tau, is a T0 space. So how? So first of all, you have to take two members from X. So let X not equal to Y belong to the set X. X means closed 0 to open 1. That means X and Y both are in this interval. So X and Y are the real numbers greater than or equal to 0 but strictly less than 1, and they are not equal. So if they are not equal, then by trichotomy law either X will be less than Y or Y will be less than X. So without loss of generality, we suppose your X is less than Y. That means the condition is this, that this 0 is less than or equal to X, is less than Y, is less than 1. This is the condition. Now X and Y are both real numbers. X is less than Y, they are not equal. Therefore, we know that between two real numbers there are infinitely many real numbers. So let us choose any one of these infinitely many rational numbers between X and Y. Let it be K. So choose a real number. Choose a real number K such that X is less than K is less than Y. And this is possible because just now I have said that between any two real numbers there are infinitely many rational, or you can say real numbers, and K is such one real number. Now look at your GK. Your GK is this 0 to K, and every interval of this type, because K is less than 1, is greater than or equal to 0, so K lies between 0 and 1, K satisfies this condition. So your GK is a member of tau, and since GK is a member of tau, GK is an open set because every member of tau is an open set, so GK is an open set. Now look at your GK contains X, but Y does not belong to GK. Why? Very simple. On the real line, here you are having 0, here you are having 1 open to this side. You have chosen two numbers X less than Y, and between X and Y you have taken K, and now you are talking of GK, and your GK is this interval, this closed to left side, open to right side, and in this interval you know that X is in this interval and Y is not in this interval, so X belongs to GK and Y does not belong to GK. So you are having an open set containing one of the elements of X and Y and not containing the other. That means your topological space, by definition of T0 spaces, it is a T0 space. So this was another question, or you can say example regarding T0 spaces, and then we will take one theorem from T0 spaces. The theorem is show that subspace of a T0 space is a T-naught space. That means the property of being a T-naught space is a hereditary property. Okay, now we'll move on to the proof of this theorem. Let X tau be a T-naught space. So we have taken a T-naught space, and now we'll consider some subset Y of X and the relative topology, or you can say the subspace topology of Y tau Y. So let Y be a subset of X and consider the subspace topology Y tau Y. And from your previous knowledge, you know that what is tau Y. Your tau Y contains the sets of the type A intersection with Y, where A is a member from tau. This is your subspace topology. This is known to you from your previous knowledge. Now this Y tau Y, we have to show that it is also a T-naught space. X tau is given to be T-naught. We have to prove that this is also T-naught. Now to prove this space T-naught, what we have to do, we will take two elements X and Y from this Y. So let X not equal to Y be two members of Y. Since X, Y are members of Y and Y is a subset of X, this means your X and Y are also members of X. Now your X and Y are members of X, but X tau is a T-naught topology. Therefore, either there will be an open set containing X and not containing Y, or there will be an open set containing Y and not containing X, because it is a T-naught space. So therefore, there exists G belonging to tau such that X belongs to G, Y does not belong to G, or there exists H belonging to tau such that X does not belong to H, Y belong to H, because of the definition of T-naught spaces. Now your X is in G, X is also in Y, so X will be in G intersection Y. And in the first case, in the second case, your Y is in Y and your Y is also in H, so Y will be in H intersection Y. So what I am going to do now, I am going to convert this G and H into G intersection Y and H intersection Y. Since G is a member of tau, so G intersection Y will be a member of tau Y. Similarly, H is a member of tau, so H intersection Y will be a member of tau Y. So that means G intersection Y and H intersection Y will be tau Y open sets now. So what I am going to say, this implies there exists G dash is equal to G intersection Y belonging to tau Y. G is a member of tau, G intersection Y belongs to tau Y, and this G intersection Y, I have named it as G dash, such that, now what is such that? This X belongs to G and this X also belongs to Y, so X belongs to G intersection Y, but your G intersection Y is G dash. That means X belongs to G dash. Now what about Y? Okay, Y is in Y, but Y is not in G. So if an element is in A but not in B, then it cannot be in A intersection B. That means your Y does not belongs to G intersection Y, and G intersection Y is your G dash. So that means Y does not belong to G dash. Or on the other side, this H is in tau, so you can say H dash is equal to H intersection Y is in tau Y, such that, once again the same thing, your X is not in H. Now okay, it is in Y, it may or may not be in Y, but since it is not in H, it cannot be in H intersection Y. So that means your X cannot be a member of H dash. And your Y is in H, Y is also in Y, so Y will be a member of H intersection Y, and H intersection Y is H dash. So your Y belongs to H dash. That means what you have obtained now. You have taken two elements X and Y from the space Y, the subspace, and you have obtained either G dash tau Y open set containing X and not containing Y, or H dash tau Y open set containing Y and not containing X, which proves that the subspace Y tau Y is a T naught space. So this means Y tau Y is a T naught space. So this completes the proof, and now we will move ahead onto T1 spaces. Now what is the difference between T0 and T1 spaces will be the basic thing, and then we will consider some examples, some properties, some theorems of T1 spaces. First of all, what is a T1 space? Definition. The definition of T1 space is very much similar to that one, the definition of T0 space. The only difference is, in case of T0 spaces, what we wanted, either a set G containing X not containing Y, or an open set H containing Y and not containing X. Now for T1 space, we want both. That means there must be an open set G containing X and not containing Y, and there must also be an open set H containing Y and not containing X. So first I am going to write the definition. Let X tau be a topological space, then we say X tau is T1 space if and only if for every X not equal to Y belonging to X, that means X and Y are distinct members of X, we have, or you can say there exist G and H belonging to tau Y. Now I'm saying G and H. Earlier for T0 I was calling G or H. Now I want both G and H in tau Y such that X belongs to G, Y does not belong to G, and X does not belong to H, Y belongs to H. The situation is, this is your X, the topology tau, and here you are having two distinct elements X and Y. Earlier for T0 space, what was our requirement? We needed either an open set G containing X and not containing Y, or if this is not there, then we wanted an open set H containing Y and not containing X to make the topological space T0. But now our need is both. That means we want G as well as H. We want G, we want H. There is a G containing X, not containing Y. There is a H containing Y, not containing X. If both these sets G and H, open sets, exist, then we say that the topological space is a T1 space. Like T0 space is also known as Kolmogorov space, this T1 space is also known as Frachet space. So this is also known as Frachet space. So now we will move on to a little bit 2 or 3 examples of T1 spaces, and then we will close this lecture here. We will move on to the properties and theorems in the next lecture. But before closing the lecture, I would like to introduce some examples of T1 spaces. So the first example which comes to our mind is of discrete topological space. So here is X and here is the discrete topology, and now you know that what the discrete topology is. Discrete topology means the collection of all possible subsets of X. So that means in discrete topology every subset of X is an open set. So if you take two elements x not equal to y in X, then obviously you are having singleton set X, this is open, and singleton set Y, this is also open, this belongs to tau, this also belongs to tau, that means G is open, H is also open, such that, so you can say there exists open set G, singleton set X, and open set Y, H, singleton set Y, such that X belongs to G, Y does not belong to G, and X does not belong to H, Y belongs to H. And that is very, very much obvious. So which makes the discrete topological space a T1 space, or you can say Frachet space. So this is the very first example regarding T1 spaces. And now we move on to another example, that means cofinite topology, you can say. So for indiscrete topology, I must tell you, if a space is not T1, if a space is not T0, it can't be T1. So indiscrete topological space was not T0, so it cannot be T1 as well. Discrete topological space is T0 as well as T1, but indiscrete is neither T0 nor T1. Now we move on to the next one, that is cofinite topology. Let X be any set and tau be the cofinite topology defined on X you can say, defined on X. Now we have to see whether this topological space X tau is T1 or not. So first of all, let us take two elements X and Y, not equal, distinct elements from X. Now look at the singleton set X and its complement, the singleton set Y and its complement. Now, is this set open? Is this set open? The first question. So this set will be open if its complement is finite. And what is the complement of this set? This is X complement, and complement once again, what you are going to get is the singleton set X, and singleton set X is finite, it has only one element. Similarly, the other set, complement of Y and complement once again, so you will get singleton set Y, it is finite because it is having only one element. So this is finite set, that means its complement is open. This is finite, so its complement is open. So these two are open sets, you can say there exist these two, you can name it G, you can name it as H, and both are now open, so they belong to tau, the topology, because every open set is a member of tau, such that what you are going to get now, this is the complement of X. So how complement of X can contain X, not containing X? So this open set does not contain X, but it contains everything other than X. That means Y is a member of this set. So you are having an open set G containing Y and not containing X, and you are also having an open set H containing X and not containing Y. So there are two open sets G and H. G is complement of singleton set X and H is complement of singleton set Y. So there are two open sets G and H, such that one of the open sets contains Y and not X, the other open set contains X and not Y. That means our condition of being a topological space is fulfilled. That means this topological space X tau, that means X is any set and tau is a cofinite topology unit. This topological space is a T1 space. So here I am going to stop this lecture. In the next lecture we will consider more and more examples on T1 space, and then we will move on to the theorems, properties of T1 space, and finally on to the T2 spaces. Thank you once again.